Okay, great. Our next speaker is Bhargav Karamched from Florida State University, who will tell us about entropic collapse.
All right, yeah, thank you. Thank you for having me. I'm pretty excited. This is a great view. First time coming here, so it's been pretty nice, and all the familiar faces. I'm excited to talk about stuff that I've been working on fairly recently. Um, so there's a phenomenon that I've come across recently in some work I've done, which I call entropic collapse. And so I'll be talking about extreme first passage times in discrete time, discrete space geometries. But to tell you the story, I have to tell you like why I became interested in this type of a problem. And so I work with a number of undergraduates at Florida State, and before going to Florida State, I never worked on any problems affiliated with ants. But for some reason, undergraduates think that I work on ants, so I started working on ants. So I'm like the ant guy now. And so I began developing models, a lattice model for spatial foraging in ants, how they form sort of these long trails that connect their nest to nearby or even distant food sources. So one of the cool things about ants is that they're very ideal for studying collective behavior within like nests. They are like within colonies, they're like literally genetically identical. A large fraction of them are genetically identical. But they have this amazing ability to coordinate activity across large distances, right? So pheromone-secreting ants, such as fire ants and Eciton burchellii, for example, perform what are called ant raids. So they'll send out foragers and to find a food source. And then once the food source is located, these ants will start secreting pheromone to attract other ants to come to that food source. And they form a trail in this way. And so their communication is through pheromones. And this foraging and trail formation process is divided into sort of two different phases. So you have this effective random walk that these ants do before they've found a food source. So that they'll do a random walk. So you get like a Gaussian-looking structure that emanates from their nest. And then once food is found, it's marked with pheromone. So they secrete pheromone, and then other ants follow them to form these large-scale trails. And when I say large scale, I mean like relative to the size of these ants, these are really large scale. So here's a famous experiment that was done in the late 80s, and again repeated in the early 2000s, of an ant. So just look at panel A here, of an ant starting at their nest, say down here, and it kind of wanders around until it finds this food source over here, and then it sort of just jets straight home. So it knows exactly where its nest is, and it can start coordinating activity across this distance here. And if you look at the scale here, like this much is like 10 meters. So this is a single ant. This is a single ant that was tracked. Went all this way and knew exactly how to get home and could, in theory, get a trail that forms from their nest to the food source. So quite remarkable. And my first project that had to do with ants was to understand how, like a mechanism for how these trails could form. Can we come up with sort of a simple model? And so the way we approached this was to treat ant as particles on a 2D lattice. And before they find a food source, they perform a random walk on their Moore neighborhood. So there are 8 adjacent sites. And then when a food source is found, and pheromone secretion starts occurring, basically this biases the direction in which they move in whatever way based on the pheromones that can be sensed. Okay, so this is how the model works, and I thought I'll just show you a video of how a potential of how, like just an output of what this model would look like. So initially you have all these ants that are going around, and then they find the food source, which is the green diamond. They start coming home, and then you have this trail of pheromone, and then the ants sort of all contract to this trail. And okay, so this was an output of the model, and yeah, okay, very cool. That was what the first undergrad wanted to do. And then after reading this paper, a second undergrad came to me and said, okay, well, now I want to use this model to try to understand how trails form when then you have multiple ants colonies competing for a common food source. And I said, okay, well, let's think about that. So ants colonies really compete for food sources. They try to avoid like direct altercations with other ants as much as possible because they're an incredible drain on resources. But you can go find, for example, if you just go look at the sidewalk sometimes, you will see this huge battles going on between different colonies, and there'll just be like decapitated ants everywhere. So here's like a photo of two ants that are fighting over a dead hornet, and then that can kind of scale into these really large scale battles. So the question was like, when these two colonies are trying to fight for a common source, like what are the factors that sort of are good predictors for success for one colony to win over the other? And it turns out like effectively competition between ant colonies is a race. It's basically who finds the food source first typically wins the food source. It's not a sufficient condition, but it's a good predictor. So typically, the first colony to find a resource typically wins the resource. That's fairly intuitive, I think. And yeah, so that was an observation from the data as well. And so this sort of naturally led to the idea of, well, okay, so we have to compute some sort of an extreme first passage time. The first ant coming from a given colony finds the food source. What are the different parameters that affect this process? And we're especially interested in these large in these large graphs, or what I mean by large graphs, in these large spatial domain type of structures, just because they can coordinate activity across these very huge spatial domains. And so I had this model, and I said, okay, let's run some simulations, try to understand what the extreme first passage time in these systems looks like. And so first I said, let's just fix the colony size and just start scaling up distance and see what the distribution looks like. And like nothing wonky happening here. I fixed number of ants at 50,000. And then if the distance is around 3 units, you get sort of a sharp peak at, well, the minimum time that a particle can traverse the distance in discrete time. And then as you increase the distance, you get sort of a distribution that forms. So nothing wonky that happens, and the distribution kind of moves away from the geodesic path, or like the shortest possible path. Okay. And so I said, okay, nothing wonky here. Now let's try to do the extreme first passage time thing. So I introduced this scaling. So I said, okay, let the number of ants multiplied by the probability that a single ant reaches the food source in the minimum number of steps. So D is the minimum number of steps. I'm going to multiply those together and say that's fixed. And I'm going to take the number of ants, to infinity, large, and then the probability that a single ant finds it for the large distances to 0. So I'm doing this extreme value scaling type thing. And I said, okay, now let's do the scaling and see what these extreme first passage time distributions look like. Okay. So if I do that, first I have a distance of 3. I get okay, and then so on the horizontal axis now I'm looking at how many units passed the shortest possible time. That's what's on the horizontal axis here. And so you get this like nice distribution. And I said, okay, now let's increase the distance. And so you have to scale up the population accordingly. And kind of looks similar, but notably the tail starts going away a little bit. The tail has sort of shrunk. And as I increase the distance even more, so I have a huge number of ants now, the tail actually just vanishes, and you get basically like what looks like 2 Dirac functions. And so it's like, okay, so the question is like, well, where's the tail going? Why is the tail vanishing? And the mechanism for this goes back to sort of the complex combinatorics that can arise on these lattices when you think about these paths. So for example, if I have a nest in this bottom corner here, and then on the same diagonal, or on a diagonal, I have a food source, there's exactly one sort of shortest path that connects the 2 points. But if I want to think about the number of paths that are delayed by 1 step, I have 12. And in this format, it's going to, if I stay along the diagonal, it's going to scale to about the distance squared. So if I increase the distance to 5, again, there's a single path, shortest path. But now there's like 30 paths that can connect it at 1 unit later. I increase it even more, the number jumps to 56, the number of paths that are delayed by 1 unit extra. And so what's happening as you increase the distance along this 2D lattice is that there's just like this combinatorial explosion that's sort of forcing any of the first arrivals of the ants to the food source to be one of the first 2 paths. First path being the shortest path, and then you get a peak at a 1 unit delay path, and then that just absorbs all the probability mass as you increase the distance. And so this is what I called entropic collapse. It's just there's just so much entropy in the system that it's forcing the distribution to be either at exactly the shortest path or just above the shortest path. There's like nothing else that can happen in these geometries. Or is there something else that can happen in these geometries? So then this sort of motivated me to ask the following question: is well, what types of geometries don't feel this entropic collapse? Right, so like, can I just sort of cook one up and it just doesn't experience this entropic collapse? So I came up with the idea of a discrete hierarchical graph that looks like this, kind of a simple graph. So there's a source of particles on the left, and then the target they're trying to reach is on the right here. And I mean discrete hierarchical because I can break this graph up into 2 pieces. There's a head, which is a connected network. And then there's a tail. And so in the head, particles will do like a random walk. They can move according to whatever they're connected to, equal probability. And then there's one node of the head that is connected to a unidirectional tail. And so on that tail, you can move forward with probability mu. So there's still like a non-zero probability that you get removed from the system. But if you stay in with probability mu, you keep going forward. And yeah, you reached your target. So these types of in this graph, for example, the entropy or where you can get sort of delayed is all within the head, and that sort of limits the entropic explosion that can happen. So this is what I started calling entropically bounded. You can sort of bound the number of paths and localize it to the head. Okay. So here's a very simple example of how the mathematics here works. This is a leaky loop example. So the head is just a single node, and you stay at the node in a given time step with probability S, and then you move to the tail with probability 1 minus S, and then mu going forward. And GT is the target. So the way I sort of mathematically quantitate or quantify this is using what I call this entropic penalty function. So D again is the distance between the source and the target, and so it's this function f of k, which sort of measures the entropic penalty for taking a detour from the geodesic path or the shortest possible path. And if you compute this, okay, so what is this ratio here? This PD plus J over PD. PD again is the probability that a single agent or a single particle reaches the target in the shortest amount of time, and P sub D plus J is the probability of reaching that target in some delayed amount of time, like a J delayed units. And you can compute this explicitly for this geometry and take k to infinity. I'm looking at this large distance. I'm looking at a large distance structure. And if you look at what this entropic penalty function looks like, it's independent of distance. So the distance, which is d, or the length of the tail, sort of vanishes from this entropic penalty function. So no matter how long the tail is, all the delay, the only thing that determines the entropic penalty is whatever's happening in the head. So it vanishes from the entropic penalty function, and then using this, you can compute the distribution for the extreme first passage time, Tn being the extreme first passage time, and taking n to infinity, you get this nice exponential function that depends in a very concrete way on the geometry that's encoded in this entropic penalty function. And then even you can get an expression for the mean extreme first passage time. Okay. Yeah, so the discrete geometry strongly impacts the distribution. And just to show you, this is what the simulations look like. You don't see the collapse here, where everything's sort of getting concentrated towards the 0 or the 1 unit delay. You do get this very nice distribution, exponential type distribution. And so I'm comparing the distribution and also the mean extreme first passage time versus the population size. Okay, so that's a very, very simple example. One head, one unit in the head, and then just a tail. Is there anything that's more complicated for which such a sort of a principle holds? That, you know, can this sort of exponential structure work for more complicated geometries? And so we can look at what I like to call the braided tail. So it's like you have the head, connected network, and then you have like n tails that are emanating out, connecting you from the end, sort of the exiting node to the target. Does a similar type of idea work here? So let's do a simple example. So this is a two braid example. Sorry for the change in notation. I changed L to D, but L again is sort of, and the picture itself is kind of deceiving. It looks like the bottom path is the shorter path. The top path is the longer path because there are more nodes. And L is like the minimum distance, the shortest path that one can take. And L plus delta is the length of the longer path, and delta is sort of the encoded delay in taking the longer path. So when you have braids such as this, you can get like really cool fractured distributions that arise for the extreme first passage time. So first, if you look at the entropic penalty function, you can compute it. It becomes piecewise defined, meaning like, okay, so the time to reach the target, if you reach the target in a time that's greater than L, but less than delta, right, then all the delays must have occurred at the source node. And then you must have taken the shorter path to reach the target. But then if the time to reach the target gets past delta, it could have been that you spent a bunch of time at the source and then took the shorter path, or you just went along the longer path. And so your entropic penalty function becomes piecewise defined. And then if you tune the parameters appropriately, you can get what I like to call a tortoise peak and a hare peak. So like in this particular example, I've taken Q2, which is the probability of taking the longer path to be way bigger than Q1, the probability of taking the shorter path. And so you get this nice peak at the shortest possible time, and then you get like a nice decay. And then when you hit the point where the sort of the piecewise structure happens, this value delta, you get this huge tortoise peak, and then you can get these really interesting multimodal peaks. And so these complex tails don't really lead to anything crazy. You still get sort of independent of D entropic penalty functions, D being the distance of the tail, and then you get like this filter of the complex N tails, which is cool. So it's all determined by what's happening in the source. Yeah.
So did the tortoise have a tail? We just can't see it. It's just like if you semi-log wide that, we would see it.
If you semi-log y, you would see it. Yeah.
But it's super small.
It's super small.
Okay.
Okay. So the key piece in these examples is this entropic penalty function f of k. So I'm going to show you, I'm going to talk about two different examples here. I just talked about the braided tail. And then another example, so I talked about the 2D lattice. Another example where you see an entropic collapse, i.e. you're not entropically bounded, is the beta lattice. I think some people say Bethe lattice, but I think it's beta lattice. So it's a tree, and this example has a coordination number of 3. This is not entropically bounded. You see the entropic collapse in that as well. And I just want to show you what the entropic penalty functions look like for each of these particular graphs. So this is for different distances. The dashed curves are for the different distances on the beta lattice. And you can see there's this very rapid divergence. There's a very clear dependence of the entropic penalty function on the distance that one is from the source. But for the braided tail, it's independent of the distance. And so this is for all 3 of those same distances. 30, 10, and 50, and it just sort of, they all lie on top of each other, complete independence of the distance. And so this entropic penalty function, FFK, gives us sort of a boundary between two different types of dynamics on networks that you can see. So there's independence of distance, entropically bounded, and then there's depends on distance, which is like entropic collapse. And these could pertain to two different types of reactions. You can sort of think of these entropically bounded structures as being like injection-limited reactions, or ones that are experience entropic collapse as being bulk-limited. So just an injection-limited process, just a biological example. For example, if you think about IFT particles in the flagellum, IFT particles have to bind to a basal body, and that's a very sort of binding, unbinding sort of process. And then at some point, they're just fired into the flagellum, at which they approximately ballistically move around the flagellum and come back. So this is like an injection-limited process. Even in action potential, you have like the chemical reactions that drive reaching the threshold or not, but once you reach the threshold, bang, you're just sort of fired. That's like an injection-limited process. And of course, a bulk-limited process, I talked about my ant model. And this is just a cool figure I found. I thought I would just put it in here. But like if you're like mRNA and you're trying to find a ribosome, that's like a complicated thing. Taking a detour away from the optimal path in such processes, at least the discrete theory says you're exposed to like a huge combinatorial explosion number of paths that you can take to get you before you get to the target. I actually have a theorem that I sort of proved in this work. So if you have a discrete hierarchical network that's entropically bounded, and you take this limit, n goes to infinity, the probability of reaching the target in the minimum number of steps goes to 0. And then the entropic penalty function will be independent of distance, as we saw in the braided tail. And then the extreme first passage time distribution will have this exponential structure. I mean, the proof is not anything magical. It's just, I don't know, it just pops out. But that is something that you can look at if you're interested in. So there's conclusions. You get like combinatorial and geometric complexity in these discrete graphs. Sort of prevents extreme first passage times from smoothing into those continuous ones that we're used to. And then there's this very cool entropic penalty function that allows us to see like the topological boundary between entropically bounded and entropic and networks that experience entropic collapse. And then so some references. If you're interested in the theorem and sort of the theoretical bits, I have a preprint. That's the first one. If you want to see how we use that theory to understand competition between the ants, you can look at this other archive preprint, macroscopic dominance from microscopic extremes. This is competition between ants. And then if you're interested in the ant model that I talked about way at the beginning, there's this Journal of Mathematical Biology paper I published a few years ago with my collaborators. First undergraduate who said, I want to learn about ants was a music major. And Sean Hartman, he's now a PhD in music theory. Don't know where he is. And then the one that wanted to use the model to understand competition is a biomathematics major at Florida State. And then Sean Ryan helps out with some of the simulations and things like that. Okay, yeah, that's it. Thank you.
Question for Bhargav?
Thanks for the talk. So I know you're the lattice man, but I'm wondering about continuous space. Yeah. If you have maybe like 1D domains, but they're like, I don't know, split, like, branched or something like that, could you extend to that case? Like,
I imagine.
Is there something about the continuum where you would lose this like tailing like property result that you had here? Like, does that rely on discreteness?
Yeah, the discrete geometry, I don't think you'll see entropic collapse, like this sort of collapse of the things to like the smallest ones in the continuum. That sort of is encoded, and it's sort of forced upon you with these discrete structures. And another bit that I didn't really emphasize in this talk, but I should have, is that the discrete geometry sort of gives you a lower bound on these time distributions, which is not necessarily the case when you have continuous space and continuous time processes. Brownian, you just take the number of particles going to infinity, they just go in the geodesic path with like in zero time, effectively.
Yeah. I wonder about like continuous analogs of these like tailing properties.
Yeah. I don't know. I don't know if you'll see it in the continuum.
Thanks.
In your case, you are scaling the probability that you take the geodesic path.
Yeah.
That is the same thing that like the continuous case does.
Yes. Yeah.
To get an actual extreme value distribution.
Yeah.
So in either case, that scaling is going to give you something that's non-trivial, right?
Yeah. You get something non-trivial in either case. But in like these 2D cases, like 2D Brownian motion, continuous time, continuous space, I believe you don't see this entropic collapse phenomenon. Yeah.
So I probably lost at some point about the measure.
Okay.
So does that relate with the extreme first passage time of the many searchers? That related?
So it encodes like it's like an entropy cost for taking a detour from the optimal path, and then it sort of shows up in the extreme first passage time distribution in this exponential. Yeah.